Hey there. So we're going to start chapter 4. This is our last unit of calculus. And we're going to start with sigma notation. So go ahead and try the warm up. You're doing 4 derivative problems here. Okay, so number 1 is chain rule. So first thing I'm going to do is just rewrite this as the cosine of 3x. And all of that is squared. That just helps me visualize this a little bit better when I go to do my chain rule. Okay, so f prime x. I'm going to bring the 2 down in front. I'm going to keep the cosine 3x exactly the same. The 2 becomes a 1, which I will not write. Next, I will do the next piece. So I just did the 2. Okay, that's done. Now I'm going to go ahead and do the derivative of the cosine. So that would be negative sine. I'm going to keep the 3x the same. And then the last thing I want to do is the derivative of the 3x, which is 3. I'm going to rewrite it just so it's a little bit nicer. I'm going to take the negative, the 3, and the 2, put them all together. So I get negative 6 sine 3x cosine 3x. All right, number 2, we have to do product rule. So we're going to do g prime of x is equal to derivative of the first, which is 5, times the second, which is secant x, plus derivative of the second, which is secant x tan x, times the first, which is 5x. All right, number 3. Number 3, we're finding dy dx, so we want to do that implicitly since the x's and y's are all kind of intertwined all throughout. So when we look at the first part, the xy squared, this is going to be product rule. Okay, so I have derivative of the first, which is x. Derivative of x is 1 times the second, which is y squared, plus the derivative of the second, 2y dy dx, times the first, which is x, minus derivative of 3x is 3. On the other side, I have the derivative of tangent, which is secant squared, 2y, times derivative of 2y, which is 2, dy dx. Okay, so to finish this problem, I want to isolate the dy dx. So what I'm going to do is I'm going to put everything that has a dy dx on one side and everything that does not have a dy dx on the other side. So I would have 2yx dy dx minus secant squared 2y. I'm going to put the 2 in front. Dy dx equals 3 minus y squared. And now I'm going to just divide. I'm going to pull out the dy dx and divide. So my final answer is 3 minus y squared over 2xy minus 2 secant squared 2y. So if you had added everything to the opposite side, your answer just would have been basically the top and bottom negated. So it would be y squared minus 3 over 2 secant squared 2y minus 2xy. All right, last one, number 4. This is quotient rule. So we're going to do h prime of x equals derivative of the top, which is 2, times the bottom for x minus 1 squared, minus derivative of the bottom, chain rule, so 2, keep the 4x minus 1 the same. The 2 becomes a 1. Derivative of 4x is 4 times the top, all over the bottom squared, so it becomes a 4. This one, I notice it could easily cancel a 4x minus 1. So there's 1 here, there's 1 here, and there's 1 here, so that will become a 3. Okay. So here I have 2 times 4x minus 1 minus 8 times 2x plus 1 all over 4x minus 1 to the third. All right, so today we are learning about sigma notation. So the Greek letter sigma is the capital letter equivalent of our capital letter S. And it stands in this case for sum. So what a summation symbol or a sigma notation allows us to do is it allows us to write the sum of many terms in a compact form. So let's just break it down. So first we have our sigma notation. That's this symbol right here. The bottom number is where we're going to start. The top number is where we're going to stop. And then this will be the formula in which we plug each number into with a plus in between each one because it is a summation. All right, let's try some examples. It will become clearer once we try some. All right, so let's look at number 1. So number 1, we're going to start at 1, we're going to stop at 11, and our formula is k squared. So on this one, I would start with 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared plus 9 squared plus 10 squared plus 11 squared. And now I'm going to stop. I'm not actually going to figure this out. This number would be very large, but that is what that means. Okay, so here's how the sigma notation works. All right, let's look at number 2. 4 plus 5 plus 6 plus 7 plus 8 plus 9. So we're going to actually write this in sigma notation. Okay, so first thing I want to do on the bottom is write where am I starting. On this one, I'm starting at 4. I'm stopping at 9. And it looks like it's just each number one at a time. So that would just be k. We're not doing anything to it or anything like that. Now, just to show you, this is obviously the simplest answer for this one. I just want to show you something. There's actually unlimited amount of ways to write this correctly. Okay, so let me just show you one other way. I could have done start at 3 and at 8 and make my formula k plus 1. Okay, this would be the exact same result. And so you can see how by adjusting my starting number and my ending number, I could actually have an unlimited amount of correct ways to write this in sigma notation. But obviously the way we did it first seems to be the simplest. All right, let's move on to number 3. So on number 3, we're going to start at 1. We're going to stop at 3, and our formula is k plus k squared. So I would have 1 plus 1 squared plus 2 plus 2 squared plus 3 plus 3 squared, and I'm stopping. Okay, this one, I think I will work it out. So 1 plus 1 squared is 2. 2 plus 2 squared is 6. 3 plus 3 squared is 12. And that gives me 20. So if I want, I can work it all the way out and get a single integer as my answer. All right, let's try the last one here, number 4. So on this one, we are going to try to write this in sigma notation. So it's 1, 3, 5, 7, 9. Okay. So on this one, I have starting with 1. I could start at 1. K equals 1. I don't want to put that I'm stopping at 9. And here's why. How many things am I actually adding here? 1, 3, 5, 7, 9. 5 things. So if I stopped this at 9, I would be adding 9 things. And I don't want to add 9 things. I want to add 5 things. So I'm actually going to stop this at 5. And to make it equal each of these numbers is where I need to adjust my formula. So it looks like I have odd numbers here, and they skip up by 2s. So I'm going to start with a 2k because I know I need to go up by 2s. But now let's just try this. If I plug in a 1, I get 2. If I plug in a 2, I get 4. And then 6, 8, finally 10. So each of those numbers is 1 more than what I actually want for my answer. So I can fix that by doing 2k minus 1. Okay, let's try that. So 2 times 1, 2, minus 1 is 1. 2 times 2, 4, minus 1 is 3. 3 times 2, 6, minus 1 is 5. 4 times 2, 8, minus 1 is 7. And 5, my final number, times 2 is 10, minus 1 is 9, so that works. So you see how sometimes you do have to be a little bit creative. Notice one strategy that I used, which was actually 2 strategies I want to point out that I used. Number 1 was I looked at how many numbers I had here, and that was reflected in my top number. Is it always going to be exactly like that? Maybe, maybe not. So you do want to look at it, but that's a good tip. Second thing was that I noticed each one of my numbers went up by 2, and I have a 2k. Okay, so both of those things are good tips to keep in mind. All right, we're going to try number 5. I would like you to try and pause the video now and try filling out this chart on your own. Okay, and then we'll go over it in a minute and you can check to see how you did. Okay, so hopefully you've tried this. Let's start with the first one. I do not have a lot of room here. Let's see. There we go. So this one looks like I'm starting at 1, k equals 1. I'm ending at 5. 1, 2, 3, 4, 5. Well, that's pretty simple. It's just k each time. And now I want the value of the sum. So 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. 10 plus 5 is 15. All right, let's try the next one. We have starting at 1, ending at 3, negative 1 to the k times k. So this would be negative 1 to the 1 times 1. That's a times. Looks like a minus. Plus negative 1 squared times 2. Plus negative 1 to the 3rd times 3. All right, so let's figure out what this would equal. So negative 1 to the 1 times 1 is negative 1. Negative 1 squared times 2 is 2. And negative 1 to the 3rd times 3 is negative 3. So this would give me total of negative 2. All right, I want you guys to put a star by this one. The reason I like this one to show you is that this is how you get a plus minus pattern, okay? And you're going to run into problems where you need to create something that has plus and then minus and then plus and then minus. That is happening right here. Negative 1 to the k. Because when k is odd, you're going to get a negative. When k is even, you're going to get a positive. So as you run through each number, it creates that pattern, plus and then minus and then plus and then minus. Okay, so that is important because you're going to have problems where you see that and you're going to go, how the heck do I get that? Here's how. All right, let's try the next one. We have our summation. It looks like we're starting at 1, ending at 3. Okay. Let's see what's changing and what's staying the same here. The top is changing. It goes 1, 2, 3. So the top is k. The bottom, 1 plus 1, 2 plus 1, 3 plus 1, that has to be k plus 1. All right, and then let's find our sum here. It's a half plus 2/3 plus 3/4. That's 23/12. All right, last one. Oh boy. Okay, this one is pretty tricky because they actually gave us these final fractions. So if you look at the one we just did, like 1/2, 2/3, 3/4, we're having to go backwards even from that. Okay, so let's just look here. it's even extra difficult because there's only 2 terms that they gave us. 16/3, 25/4. All right. So let's just say that the bottom was 3 and 4 and not change. The top of the 3 is 16. The top of the 4 is 25. What sticks out to me is that both of those are perfect squares. 16 is 4 squared, 25 is 5 squared. How am I getting that? Well, if I take a 3, I need to add 1 to it and then square it. If I start with a 4, I need to add 1 to it and then square it. Okay, I think I've got it. So for this one, my summation would start at 3 and at 4. This might be the first one we have that doesn't start at 1. Oh no, we had example 2, started at 4. Okay, start at 3, end at 4. K plus 1 squared on the top, K on the bottom. Okay, there are other ways we could have done this. We could have made the top K squared and the bottom K minus 1. Then we would start at 4, end at 5. Okay, so it's really multiple ways to do it. All right, let's take a look at some rules. Number 1, sum rule. Just saying we can break up a summation with an addition. We can create 2 problems out of it, do them separately, and then add them. Same thing with difference. Constant multiple rule, meaning we can pull out a constant and just multiply the final answer by that constant instead of having it in each part of the problem. And then number 4, constant value rule. Okay, this is a good one. This is a handy one. This says if your formula is just a number, just a plain number. So let's say we had the summation from 1 to 5 and all that was here was an 8. There's no K. This says the answer is just the final value, so in this case the 5 times that constant 8. Wow, that's so much easier, right? Than having to work it all out. Why is this true? Because each time all I'm writing down is an 8 and I have 5 of them. Okay, 5 eighths is 40. All right, I hope this is making sense to you. This is one of those things that, is it really all that difficult? No. But guess what? It looks really difficult because it's this crazy symbol. So this is one of those things that you can do on your kitchen table in front of your family, and they're going to think you're like really, really, really a genius. All right, let's look at number 6. This is the last one, and then you guys are going to do your homework. It says, show that the sum of the first n integers is summation from 1 to n of k is n times n plus 1 over 2. This is a formula. We are going to use this formula. It is super handy. Okay, so I definitely want you to remember this formula because it is so handy. Because what this means is if I gave you a crazy sum, like 1 to 100, instead of you having to sit there and go 1 plus 2 plus 3 plus 4 plus 5 and go all the way up to 100, all you have to do is plug the 100 into this formula right here and you're going to get your answer. Okay, so a super, super handy formula. If you can remember that it's there, you can use it and it saves you a ton of time. All right, so we're going to actually prove this formula. All right, so the first thing we're going to do is let's just see if it works. Let's just show that it works. So we're going to pick a pretty small number. We're going to try 4, n equals 4. Let's just try that. Okay, so we're starting at 1, ending at 4. So let's actually work this out. So it would be 1 plus 2 plus 3 plus 4, that's 10. And if I try the formula, so n is 4, so I would have 4 times 4 plus 1 over 2. Well, let's see. 4 times 4 plus 1, that's 4 times 5. 20 divided by 2 is 10. Okay, so it does work in this case. We didn't prove it is always going to work, but in this case it works. Okay, so now we're going to show it generally. So keep what I just erased, but I want you to have what we just wrote. I can't fit everything. So now we're going to just show it for n. Okay? All right, so for n, let's just think about what this would do. Now remember, we don't know where n is. It could be any number. So for n, we would start at 1, plus 2, plus 3, plus dot, 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 plus n minus 1, all the way up to n. All right, so what we're going to do now is we're actually going to add this same thing again to itself, but we are going to add it backwards. Okay, so I'm going to start on the bottom with n, and then n minus 1, n minus 2, dot, 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 all the way down to 2, and then 1. Okay, when I do that, let's start from the beginning. I'm adding vertically here. So the first one, I have a 1 and an n. That's 1 plus n. Next one, I have 2 plus n minus 1. Well, that's 1 plus n again. The next one, 3 plus n minus 2. 1 plus n again. And it's actually going to keep being 1 plus n. It works all the way down even at the end. Okay, well that's pretty cool. So what I have here is I have n 1 plus n's. Okay, so here I have n 1 plus n's. Okay, so I have n 1 plus n's. But I doubled this, right? So I was only supposed to be finding the sum of this, and I gave myself 2 of them. So to undo that, I need to divide by 2. So let's write over here, n 1 plus n's, but double what I want. Okay, so that is why the summation from 1 to n of k is equal to this formula. And like I said, if you can remember that this formula exists, it is going to save you a lot of time. All right, homework is 2 pages. Some of them are multiple choice. So some of them you are just evaluating things. Couple ones I want to point out to you. If I'm looking at number 2 here, if you look at A, remember the rule that says you're allowed to pull out a constant. Okay, so if you want, you can pull out that -2, and then you're left with the formula that we just did, right? Because it would just be a k in there. So you can do the formula and then times it by -2. Another one I want to point out to you, C. That is the formula, but you do need to be careful because it starts at 9 and not at 1. So what you can do is you can minus 8 from the 9 and the 36 and then use the formula. Okay? And then on C, if you do that trick by minusing the 8, just make sure that you add in an extra 8 28ths that you're taking away. Okay, so that's important as well. And then on D, this is the constant, it's rule number 4, constant value rule. So remember that one as well. That makes that one a little bit easier. All right, so go ahead and try these. See if you can get to C with the trick that I told you. It's a little bit tricky because you do have to minus the 8 off of that. So just try it and see. You might want to do it both ways and see if you can get it to work.